We're now going to take a look at a differential operator that would annihilate each of the following functions listed in 7. So if we have things like exponentials times cosines or sines, or if we have kind of like the largest combination that we're looking at, which would be polynomials or in general powers of x times exponentials times cosines or sines, then the following differential annihilator would annihilate these functions. It's going to be the second derivative minus 2 times alpha times the first derivative, where alpha is, again, that's going to be the coefficient of the exponent in the e term, plus a squared plus b squared, where again alpha is as described before. Alpha is the coefficient of the x term in the e, and beta would be the argument of either a sine or a cosine function. And then this is going to be to the nth power, where again n is one more than the highest power of x that would appear. So if we had like an x cubed, then n would be 4. If we had an x to the 7th, then n would be 8. This differential annihilator this differential operator annihilates all of these functions. To see why that's the case, to see where this is coming from, again, it kind of goes back to what we described earlier in terms of, solutions to the homogeneous equation. So let's suppose if we looked at the case when we had like real repeated roots, we recall that the repeated roots of a auxiliary equation, they come in complex conjugate pairs, not repeated roots, complex conjugate pairs. They'd be of the form alpha plus IB and then alpha minus IB. If these are both of multiplicity n, then we can say the following thing. So if alpha plus IB and alpha minus IB, so if these had multiplicity n, then that would mean that m minus alpha plus IB would occur as a factor n times, and m minus alpha minus IB to the n would come from this. We could pull out the power of n. We would have m minus alpha plus IB times m minus alpha minus IB. Take the product on the inside, which would probably be easiest if we do it like this. I can distribute the negative sign in, m minus alpha minus I, I don't know, I'm calling it b, it's beta, m minus alpha plus I beta, and then associate the real parts together. This is m minus alpha minus I beta times m minus alpha. You don't have to do this, but it makes the multiplication much easier because that turns it into a product of sum and difference. So the result would be the difference of the squares here. So we would get m minus alpha squared minus I times beta squared. And then when you expand this, you see where that term is coming from. It's going to be m squared minus 2 alpha m plus alpha squared. I squared is negative 1, so that's going to change into a plus beta squared. And now it's to the nth power. And this is that expression we saw in the textbook. They didn't show where this came from, but you're just assuming that these have multiplicity n, and working backwards, that would lead us to that differential equation. So this differential operator will annihilate all of these expressions. Let's take a look at one together. Let's find a differential operator that would annihilate 5e to the negative x cosine of 2x minus 9e to the negative x the sine of 2x. So we look at these terms. The one thing that's kind of convenient is that the cosine and the sine both have the same argument. And the type of differential operator we're looking at, as we said a moment ago, it's going to be of the following form. So it's going to be of the form d squared minus 2 alpha d plus alpha squared plus beta squared to the n. I won't expect you to memorize this. I will post this along with one of the other screenshots in the D2L notes section, so you can quickly refer to it as needed. Recall alpha is the coefficient of the x term, the coefficient of the exponent in e to the x. So alpha is -1, and then the beta term would be equal to the argument of the sine and the cosine, the coefficient of that argument. That's going to be 2. And then for the n, we don't have any x terms out in front, just a bunch of constants. We have 5 and 9. Constant functions, we can think of polynomials of degree 0. So the order here has to be of one more degree, so it's going to be to the first power, which means that the differential operator is going to be d squared minus 2 times -1d plus -1 squared plus 2 squared to the first. This should be the differential operator that's going to do the trick. That's d squared plus 2d. This would become plus 5. -1 squared is 1. 2 squared is 4. 1 plus 4 is 5. And then the whole thing is to the first power. So this differential operator, L equals d squared plus 2d plus 5, that would annihilate this function. Let's actually go ahead and verify it. We haven't seen an operator of this type. It's kind of new to us. So there's no harm in checking this one. So let me apply L to that function y, if I call this y equals. So I'm going to apply d squared plus 2d plus 5 to 5e to the -x cosine of 2x minus 9e to the -x sine of 2x. So this is going to be equal to, we need to take the second derivative of each piece. We need to do twice the derivative of that function. Oops, sorry about that. Come on back. There we go. And then we need to add 5 times the original function. And now maybe I'm regretting a little bit verifying this, but it's no big deal. We'll work through it here. It's going to be a ton of writing. So the second derivative, again, that's the derivative of the first derivative. If I do one derivative of this thing, it's going to be a product rule. I'm going to get a -5e to the -x cosine of 2x. Then we're going to get a -10e to the -x sine of 2x. The first derivative of this piece would be plus 9e to the -x sine 2x minus 18e to the -x cosine of 2x. That looks good. And you can kind of cheat a little bit here because this is the derivative. We just did the first derivative in order to get the second derivative. So I'm going to write this down pretty quickly. This is going to be plus this is the first derivative on the inside of this parenthesis right here. I need to double that. So I'm just going to write down twice all of these terms on the inside. That's going to be a negative 10 e to the negative x cosine 2x minus 20 e to the negative x sine of 2x plus 18 e to the negative x sine of 2x plus 36 e to the negative x cosine of 2x, and then we have plus 5 times the original function, 5 e to the negative x cosine of 2x minus 45 e to the negative x sine of 2x. Before we differentiate this part again, let's do some cleaning up. Got a huge mess right now, but it's not too bad. We're almost there. If I look inside of this parenthesis here, let's combine our cosine of 2x terms. That should give us a negative 23 e to the negative x cosine of 2x. And if we combine our e to the negative x sine of 2x terms, that should give us a negative e to the negative x sine of 2x. And then let's also see what's outside of the derivative that we can kind of combine. So we have a bunch of negative e to the negative x cosine of 2x terms. Let me just kind of highlight those coefficients. We have negative 10, negative 36, and positive 5. That should combine to give us, let's see, negative 46, negative 41, e to the negative x cosine of 2x. And now we'll combine our negative e to the negative x sine 2x terms, coefficient of negative 20, positive 18, and negative 45. If we go ahead and combine those, that's going to give us a negative 2 plus negative 45 would be negative 47 e to the negative x sine of 2x. Okay. And now we're going to take this last derivative, and we hope everything gets annihilated. Shouldn't say hope, we know it's going to. It's not a matter of hope, just a matter of prudence and careful calculation. Okay, so we're now going to take this derivative. That's going to involve the product rule. We're going to get 23 e to the negative x cosine of 2x, and then a plus 46 e to the negative x sine of 2x. That's using the product rule in this first term. Now we need to differentiate this term. We're going to get a plus e to the negative x sine of 2x, and then a minus 2 e to the negative x cosine 2x. Minus 41, so don't forget we need to copy these parts down, minus 41 e to the negative x cosine of 2x minus 47 e to the negative x sine of 2x. And let's go ahead and combine like terms. Let's start with the cosine, the e to the negative x cosine of 2x terms first. There's one here, and one here. Well, that's a dud. They don't combine. Hold on one second. The e to negative x sine of 2x terms, those do cancel. So we have one here, and one here. 46 plus 1 would be 47, and then 47 and negative 47 would cancel. So those cancel. And I must have dropped, unfortunately, sorry, but I dropped the sign.